Assalamualaikum and good morning. My name is Alif Daniel bin Aminasi, and I will go to the problem we set out to test for our good project. So for the first one, MPI, which is a message passing interface, is the standard way to split work across multiple machines, but is normally run on dedicated high-speed data center network. So we instead built an MPI cluster from four ordinary Windows laptops connected only by a shared wireless mobile hotspot. So the central question, does splitting the same analytic workload across four laptops over Wi-Fi actually make it faster than running it on one laptop alone? So we expected at least some speed up, even a modest one, when once more nodes join the cluster. So as we can see here, for the typical MPI cluster, it has a dedicated servers, wired gigabit/InfiniBand, and low stable latency. And then for our setup, we only use four laptops, shared Wi-Fi mobile hotspot, and it has a high and variable latency. So next is objective. So there is a four objective that we want to achieve in this project. So the first one is to implement sequential and MPI version of 6 analytical tasks, which is a statistic, histogram sorting, correlation, moving average, and outlier detection. And the second objective is to set up and configure a working 4-node MPI cluster across physical laptops connected over a wireless hotspot. And the number 3 is to measure and compare execution time, speed up, and parallel efficiency between the sequential and MPI version. And for the fourth objective is to explain the result using Amdan law and quantify how much of the difference is caused by network communication overhead.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amirul Istiqamil. Today I'm going to continue the presentation. We're going to system setup master web worker over Wi-Fi. We use 4 Windows laptop in our master and worker layout. All 4 laptop are connected through one shared wireless mobile hotspot. When we try to connect it had a Windows security block, which is error fast access denied, launching remote MPI jobs. We fix it with a shared admin account. So every server scale out, get back, control the one hotspot box in the middle of the diagram. Next, we're going to experiment setup. We use fixed dataset, which is 100 million static floating point value. And we have 6 analytical tasks run twice. First, once in sequentially, and another one is distributed via MPI. Then we have 10 binary dataset tests at 1, 2, 3, and 4 MPI nodes. Our goal is isolate the effect of editing node with everything else at constants.
Assalamualaikum and hi, my name is Muhammad Faris bin Muhammad Razi, and I will continue the presentation on result more nodes much slower. The sequential baseline 2069 millisecond expectation MPI should beat this as nodes increase. Reality 4 node MPI took 72,137 milliseconds, about 35 times slower than sequential. Even one node was 1.6 times slower than sequential, purely from MPI startup overhead. The red hatchet segment on the right side is pure network overhead, and it grows fastest of all as nodes are added. Over here we can see the graph of the project total execution time composition by task across cluster configuration, where the 4 nodes is much more millisecond need. Moving on to result, the slowdown is an event. Sorting 1,451 milliseconds sequential to 25,568 milliseconds on 4 nodes. Moving data outweighs any benefit of sorting smaller chunk. Basic statics 24 milliseconds to over 25,000 milliseconds. The math is trivial. Almost all that time is the network scatter. The other 4 tasks reuse data already sent to each node, so they stay fast at every node count. For log scale needed, task time spent 4 orders of magnitude from under 1 millisecond to over 25,000 millisecond. Over here is the bar graph for per task execution time, sequential baseline versus 4 node MPI cluster. As you can see here, basic statics, sorting, Pearson correlation and outlier detection is conquered by MPI 4 nodes, while histogram generation and moving average is from sequential.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nick Nasha bin Shauki, and we will be moving to efficiency collapses per task, which measures how much of the theoretical 4 times benefit of each task actually captured. The dashed line marks 100% ideal linear efficiency. As you can see, almost every task sits below it, down in the single digits. The only task that exceeds 100% is the histogram generation. However, that's just a side effect, not a real win, because it inherits data that was already scattered by the. Now moving on to Amdahl's law. Classical Amdahl's law assumes communication is free, meaning it always predicts a speed up of at least 1 times, but our measured speed up falls well below 1 times at every node count, which is something Amdahl's law alone cannot explain. The shaded region between the two lines isn't an error, it's the actual communication overhead visualized. The conclusion here is that the wireless network controlled the performance, not the algorithms or the CPU. To conclude, our 4-node MPI cluster on a shared Wi-Fi hotspot ended up being up to 35 times slower than a single sequential program. The algorithm correctly used standard MPI patterns. So the root cause was the roughly 80 megabytes of network transfer per task. Our main recommendation is to replace the wireless hotspot with a wired Ethernet switch, which we will expect to flip into a genuine speed up. Finally, the dataset scaling tests for the 1 million and 100 million elements are still pending, making them the top priority for future work.